So it's my pleasure to introduce you our today's speaker, Eduardo Barredo. He comes from Mexico and recently finished his master studies in the National Autonomous University of Mexico, right? And now he joined our group doing some stuff on topological, on Axion electrodynamics, but then some stuff topology as well. So he will tell about his master project, which he did in Mexico, devoted to Cherenkov radiation in Weyl semimetal. Eduardo, please, the stage is yours.
Much move here and use pointer.
You can use a pointer so that there is a letter. If you love it. It's so easy. Yeah. So you press the button. If not, then we may do like this.
Okay, thank you. Well, hello everyone, thanks for joining the seminar today. As Professor Maxim told you, I will talk about my previous research work that I did during my master's in Mexico at the National Autonomous University of Mexico. And it will probably at any time during the presentation. So next step. First, let me give a brief introduction to the topic. So, in the 90s, Carroll-Field-Jackiw proposed a modified Lorentz violating theory of electrodynamics that consisted in adding an extra Chern-Simons term to the invariant density. That this Chern-Simons term coupled the dual electromagnetic tensor F, constant for vector B, and the gauge potential A. This model breaks Lorentz symmetry explicitly because of the constant for vector, and both preserves gauge invariance. The gauge invariance, one can see that it preserved if one make a gauge transformation on the gauge potential A, and then by parts the integral of the action, one can take out total derivative, which doesn't affect the equation of motions or the equation of one of them in this theory. So the resulting equation of motions are given by this equation here. Remarkably, this theory describes the electromagnetic response of what we call Carroll model. And a particular case of Carroll model are semimetals that maybe it doesn't look in the very well in the presentation, but the Lorentz violating coefficients B corresponds to separation between the bimodes in momentum and in distance. And well, this theory from the equation of motions, one can obtain a modified set of Maxwell equations that are known as Carroll-Field-Jackiw equations, where the extra terms in red, one can identify them as extra charge or current density that can appear after one applies electromagnetic fields, external electromagnetic fields to this type of medium.
Nice, a bit main question. So you're saying that this is Lorentz violating theory, but it seems that everything is in four-dimensional form. If you switch to another reference frame, just transform back to B, it seems.
Yes, the Lorentz invariance is not about yes. You're breaking the rotation symmetry when you have the vector B, and the boosts when you have the B0 component. These are the Lorentz symmetry that you explicitly break because of this. Let's say this permeable fields that are constant in describe this kind of.
Yeah, but let me ask a further question. So assume you are dealing with the Weyl semimetal with B0 equal to 0, but then you consider the fields in the moving reference frame. Would you get non-zero not in that case. So moving wires and
I would say that probably not, but because these fields are constant, maybe it moves in reference frame, they constantly repeated, for example, say the same to make it zero. But you mentioned this zero problem. I don't know. I don't know.
Can we go to the discussion?
Yes. But not only the gauge invariance is preserved if the vector is constant, also is preserved if it has this form. If it comes from a gradient of an axion of an scalar field. So this is the connection of the CFJ equations to the Axion electrodynamics. When one considers that the components the components of the vector B actually come from the derivative of a scalar field that can be theta. So the Lagrangian that describes the Axion electrodynamics are of this one and was proposed by Wilczek in 1987. And actually, this model also preserves gauge invariance, obviously, because you can see all the components of the Lagrangian density are gauge invariant. And this model, or the actions were proposed to solve the simple problem in quantum thermodynamics, but generalized series of actions can have couplings to photons, and enables this emergent electromagnetic response in Axion matter. For example, but this is for the particle physics sides. In condensed matter, the Axion field has like realizations and actually describes matter. For example, Axion electrodynamics can be represented as a particular case of a medium characterized by these constitutive relations, and we can see that these constitutive relations corresponds to telegal media, also known as magnetic media, with permittivity and permeability equals to 1. And not only telegal media, this theory also describes electromagnetic response in topological insulators, which is when the Axion field is quantized. Magnetic media, which when the Axion field is non-quantized or is a constant. Chiral matter, our case. And recently in metamaterials, we can have synthetic Axion, emergent synthetic Axion response in some artificially structured sites. Okay. You may ask what I mean by chiral matter. Well, chiral matter, we defined it as matter that exhibits chiral transformation. So you have these two anomalous quantum effects that are like for the anomalous Hall effect and the chiral magnetic effect that appears in these type of materials, but the underlying phenomena that produces these quantum anomalies quantum effects is the chiral anomaly, which is the non-conservation of the chiral transport currents. But for example, examples of chiral matter, not only the semimetals, the formation of semimetals, but also the quark-gluon plasma and the hypothetical Axion that matter. In the quark-gluon plasma, the D0 component does not correspond to specifically to a separation between nodes in energy space, but it's related to something that's called chiral imbalance, which is the difference between chiral fermions between left-handed and right-handed chiral fermions. This produces a chiral imbalance and allows these emergence transport currents when you apply a magnetic field.
Good question. So when speaking about chiral transport, do we mean that somehow particles with the spin up and spin down are transported different, roughly speaking? Or in the case of photonics, left and right circular polarizations are transported different.
No, it's about fairness. It's about particles that has different chirality. But maybe
polarization
if you is pseudo particles. Maybe if you have pseudo particles,
okay, good. And then my question is photonic spin Hall effect an example of Carroll-Field, or it's something different?
quantum Hall spin effect.
Quantum spin.
Well, it appears in a number of effects, so I would suggest example.
We should distinguish. Some people are saying these are Carroll H states, these are Helical H states. So in the case of photonic spin Hall, as far as I understand, people are talking about Helical H states. So you have a pair of H states with different X-ray spins, different polarization, propagating in the different direction. But it seems like, at least from this slide, that it also falls into category of Carroll-Field.
I haven't thought about this photon radiations of this.
Yeah, but we can look at solid state. Let's take solid state realization. You have spin up electrons going clockwise and spin down electrons going counterclockwise. Does it satisfy the definition of Carroll-Field, or it's something different?
You have to have many body system with a lot of these particles with different with left-handed and right-handed chirality. That's what I mean. And this is a two-dimensional setup, right?
Yeah, we can imagine.
But what I mean in chiral transport phenomena in this case is three-dimensional materials that is constructed from chiral fermions, which, for example, is the example of the quantum plasma. Probably you will have an electromagnetic response in two dimensions, but the equations that describe these two-dimensional structures probably should be different.
Okay.
This is for three-dimensional materials. Yeah. And well,
sorry, can I say? Yeah, I didn't quite understand. So this initial equation for reaction. So what this to reason to describe some properties of some media or some theoretical proposal.
Well, initially the Axion electrodynamics was a theoretical proposal to solve a problem in heavy physics. Later, it was discovered that you can have this Axion heavy in realizations with condensed matter. And these Axion fields describe topological materials somehow, with some emergence of Axion response, depending on its quantized field, non-quantized field, gives a response like Carroll matter, and so on. Firstly, it was just a proposal to solve a problem, specifically in analysis.
So you say that they violate some warrants.
In the case of Carroll matter, Lorentz symmetry is explicitly violated by these vector fields that are constant. So what I mean is that, for example, the vector B was violated explicitly the rotation symmetry, because you have a preferential direction, and this can happen in a conventional system because that's what is for example, the materials based on refraction. So
yeah, but so this doesn't break the principles like a selective reference frame associated with this. And that's why usually the equation of electrodynamics will look differently either in the frame associated with this material or in the frame moving with this vector. That's why no contradiction. Essentially, what are some metrics we do? So the effects there are also huge.
So they describe this Weyl semimetal.
Yes.
And this, so the response is described by these quantitative relations.
Yes.
And just also a small question. So when you have key vectors, it is equal to something that is there a problem that E is a polar vector or it's called actual, yeah, actual vector. So I mean, how do you sum this to different vectors?
What do you mean by electric polar vector and these?
I'm saying that E and P are transformed differently on the inversion.
Yeah.
So how do
Okay.
we plug them?
They actually belong to a transformation. Yes, sir. It's PTO. Yeah. Good question. So actually, it's important to say that the CFJ-model is corresponds to the CPT-odd term of a model called standard model extension, which is also a Lorentz violating theory of electrodynamics, where it includes the CPT-even and CPT-odd terms. CFJ-electrodynamics correspond to CPT-odd. This model was proposed to fund the search for possible installations in physics. For example, the CPT and also have realizations in condensed matter. The CPT term describes an anisotropic and birefringence material, and it has been studied that it produces a splitting of the Cherenkov radiation into parts, which of course corresponds to different polarization modes that are related to this splitting of this ligand. And the CPT-odd, which was proposed initially to handle physics, it is known that allows forbidden processes such as the vacuum Cherenkov radiation, because the dispersion relations is different in this case.
So what is this KF? Is this?
Oh yes, this is the terminology they use to propose this SME standard model extension. And the KF is the CPT term, and the KAF is called CPT term. And they are proportional. Our vector B is proportional to the KAF CPT term.
And in the case of anisotropic interaction, media is four front tensor is somehow constructed from anisotropic itself.
Yes. So we have seen that there's some stories on Cherenkov radiation, so it's reminded by this Cherenkov radiation. Since discovery, it has played a major role in the study of high-energy nuclear and cosmic ray physics. And it helped to design particle detectors such as the rich detectors. And let me remind you that it occurs when a particle travels faster than speed of light inside the medium. And I want to highlight that the direction of the radiation is always in a forward column. It goes in the direction of the velocity of the particle. And the direction is given by the index of refraction of the medium and the velocity of the particle. But in unconventional media, like magnetic media, topological insulators, materials, for example, the Cherenkov radiation can have richer and more interesting properties. One example is the reverse Cherenkov radiation that can appear, it is found that it can appear in 3D topological insulators. This is a work that my group in Mexico did when they studied the radiation of a particle that is traveling between two magnetic media or topological media with different parameter theta And they find out that in the interface, in addition to the Cherenkov cones to the cone that goes forward, it appears a second Cherenkov cone that goes backwards.
Let me ask a question here. So if you are investigating the geometry with the boundary between the media, here you get also transition radiation. So how would you separate this?
Because the angle of radiation of the second cone is it's very well defined. They also made another study of transition radiation if you're interested, and they calculated the transition radiation of this transition between this media and the second media. So they differentiate these two types of radiation because one of them, in this case, is very well defined with a specific angle.
But is the trial that both theta 1 and theta 2 affect the second chain?
Yeah, and actually it has a proportion of the difference between these two, the square, I think. And actually this second Cherenkov cone is very suppressed with respect to the forward cones. It's smaller in quantity, but it appears.
Good, but then a small follow-up question. What if we create a continuous gradient of this theta? Then we should get the second Cherenkov cone, and this brings us directly to the fourth gradient, right?
No, that's what we thought, but it doesn't appear. There's this Barredo Cherenkov point. Somehow, because there is a gradient very, I don't know. I don't know why, but it doesn't appear this Barredo Cherenkov.
Yeah, but here the effect is proportional, as you said, to the squared difference theta 1 and theta 2.
Something like that, yes. I don't have the number. Yes.
Maybe this might answer, because if you had just the first power of difference theta 1 and theta 2, then it can combine into the derivative, and then you can consider the case with the solution gradient. But here it might just the effect might vanish.
I haven't thought that too.
Yeah.
Okay, yes.
But at least you understand the
yes. Yes. Oh, thanks. Okay, so this phenomenon is analogous to the reverse Cherenkov radiation that happens in left-handed materials and was studied by this guy, Deselago, in the 60s, and finally got an experimental detection of this effect 40 years later. In the first metamaterial structures were studied, and because in metamaterials one can have materials with index of refraction with negative index of refraction, and yeah, so okay, so the motivation is here, and since we have backward Cherenkov radiation in topological insulator, that indicates there is richer bending energy in radiation in electrodynamics. Also, Cherenkov radiation based on biosignators could be useful to detect particles to detect particles. And also, since axions are now considered a very promising candidate for dark matter materials with effective action response, with effective electromagnetic action response, will play a major role in these searches for this dark matter, and by exploiting the electromagnetic properties. That's why they are interesting right now. So we ask ourselves how this electromagnetic radiation modified within chiral matter. So we use a gain function method so in order to be this method applied to other sources, not only the case of Cherenkov radiation. And we applied the result to Cherenkov radiation because it was known that it had these richer effects. So this is the outline of the talk. Now I give the introduction. I will give some results of the CFJ dynamics that are known. I will present the gain function method we use, and in the final case, I will give you some results with the Cherenkov radiation case we studied. Since we are modifying the electromagnetic, the electrodynamics, the Maxwell equations, well, the energy momentum density is also modified by this term. So the energy density is also modified, and the energy in this case is not positive, definitely. So this will bring some instabilities in the theory. This will prompt us to choose the B0 component equal to 0, not only to simplify the calculation, but to avoid these instabilities that are in the theory. Also, one can calculate the energy flux in this theory that corresponds to the Poynting vector in this medium. If we make B0 equal to 0, then the Poynting vector remains the same as usual. So we can calculate with the Poynting vector the distribution of radiation and then calculate the angular distribution of radiation for any. Also, the propagation of electromagnetic waves inside Carroll matter is different by some cases. When B0 is equal to 0, if B0 is different than 0 and the vector B is 0, you can have two circular polarization modes. This medium is birefringent. But if B0 is bigger than CK, then the left-handed mode is not propagating. You can see from the dispersion relation. And the positive rule is unstable because it grows exponentially. We don't like that. So in the case when B0 is equal to 0, you can have two elliptical polarization modes, left and right-handed. It corresponds to a birefringent and an isotropic medium. But both modes are propagating and there is no instability. That's what we like. And if we have this dispersion relation, when we have made the vector B goes in the Z direction, just to simplify the dispersion.
That's all that I ask you. So if B0 is small enough, do you still expect some stability?
No.
But in the previous slide, you told us that energy density.
Because yes, of course, somehow if B0 is large enough, maybe it can introduce some problems. So we have to avoid these problems. But and if you consider both B0 and B, then I haven't point here because I didn't find the expression relation that I calculate, but it appears that you don't have instabilities, but it's very, very hard to calculate the Green's function. So when you have both, probably you can avoid these instabilities. I don't know yet. Maybe we will make some research about this in the future. The Green's function method. Well, we start from the Lagrangian and calculate the Euler Lagrangian equations. And by writing the CFJ equations in the covariant form, in terms of the gauge potential, we can have this very nice equation where the box operator is the D'Alembert operator, J mu is the source current, and this epsilon is the Levy capacitance. So we can express the solution of this equation with the Green's function in momentum space. To do this, we have to use charge conservation and gauge invariance and obtain this nice Green's function in the Chi space. But also, I told you that I will make B0 component equal to 0 and the vector B goes in the Z direction. So we need to integrate this Green's function in the Chi space to express the gauge potential in coordinate and frequency space. Well, so much better. Yeah, you can see that the gauge potential in yes. Yes, well, just a little bit better. So we have to integrate this Green's function in K space. But I will show it to details because I lost you in the road. So you just need to know that the Green's function is calculated in the partial approximation, and we use another approximation that is taking this parameter beta. That this beta is proportional to the vector B. The full Green's function is that one. Remember that I told you that the polarization modes are 2. So in the eta, in the subindex eta is captures I think, captures some of the polarization modes because you have theta +1 and +2, and the +1 term corresponds to right-handed, and -1 corresponds to left-handed polarization modes.
Is what does C sub eta correspond to the refractive index?
Yeah. Yes, but when theta is 0, and we will see it afterwards. Yes, it's related to the index refraction. We make a lot of approximations here, so you have to believe me that this is the index, the Green's function that we obtain. Once we have the Green's function, we can calculate the potential fields, the gauge potential fields, using the Green's function for any source, just by integrating the sources around the localized trajectory with this integral. So once we have the gauge potential for an arbitrary source, we can calculate the electromagnetic fields very easily, and then since the Poynting vector is the same because we made B0 equal to 0, we can obtain the distribution of radiation for any arbitrary source. But I won't show you the distribution because it's better to apply this method to a particular case to see some nice effects.
Yeah. So, but then the following question. So, if we assume that our sources are distributed the plane, so we have the whole plane filled with the currents oscillating in time. So, do we reproduce with this method plane waves propagated? So, how do we produce normally the plane waves? You create the plane with the currents, and the currents are oscillating in time. So you can substitute such a distribution of currents here. So do you get the plane wave modes of these wells?
Okay, yes. The electromagnetic fields have plane wave, somehow plane wave structure, but we haven't, and this is still a point of research because we want to know, like for sure, that these electromagnetic fields we find, this in particular the electric fields, is a plane wave, and the polarization of this electric field will tell us more about the polarization of this radiation we have. I would say I'm like 80% sure that it's plane wave. And Leta term, if this electric field that appears when you calculate the electric field is left or right-handed polarized.
It could be a nice consistency.
Yes.
Especially if your refractive index matches that which you found on the previous slides.
Yeah, we need to do that. We will do it. So, like you might notice, we have considered the case of when the index of refraction is n is equals to 1. So this, if we calculate the Cherenkov radiation now, this will be the case with the vacuum Cherenkov radiation I showed you earlier in previous studies. And semimetals and Carroll-Field as well doesn't have index of refraction equals to 1. Actually, they are bigger than 1. So, but to consider this, we have to make these replacements to all the quantities we have calculated. And one can obtain this from just the Maxwell equations of a non-magnetic Chiral material. So you have to believe in this, and we have to make these substitutions to obtain the Green's function of a chiral matter with index refraction different than 1, bigger than 1. So we apply our results for the Cherenkov case. We consider first a charged particle traveling parallel to the vector B. We consider an interval, a traveling interval between this parameter xi, minus xi, and 2 xi. So the traveling current densities are these ones here. That depends on this function here, this psi function. And let me do the calculation, but the spectral distribution per solid angle is given by this expression here. So one has to notice that the important thing of this distribution of radiation is that these time terms, when you make the parameter psi go to infinity, behaves like a Dirac delta. So they gave us the direction of the radiation. And so we have two different directions of radiation. And this gives us the Cherenkov radiation condition given by the function, the C function that we have presented earlier, maybe you remember. But the Cherenkov radiation condition is this one. So from this Cherenkov radiation condition, we can know that we could have up to 2 cones given by theta plus and theta minus, described by eta plus or theta minus in this function here. So Cherenkov radiation will be real if the velocity of the particle overpasses this threshold here, this inequality. So by analogy to the standard Cherenkov radiation, you can argue that the Carroll material produces an effect. The Carroll matter, it produces an effective index of refraction for each cone. And the effective index of refraction is that one here. So the index of refraction that each cone feels is different. So we have birefringence. And that's what I told you that each cone corresponds to a different polarization. We can numerically calculate the possible Cherenkov cones for a specific case. For example, this one. We have 3 cases. The first one, and I put another theta that corresponds to the case of the conventional Cherenkov radiation when we have the beta term equals to 0. Just to a comparison with our Cherenkov cones. So imagine we have a particle with 0.45 the velocity of the light and an index of refraction of 2. Even though in conventional model you won't have Cherenkov radiation, if you have this Carroll material with index of refraction 2 and a beta equals to 0.5, you will have Cherenkov radiation. And the angle is invariant, so it's given by this number. There is another case when you know you will have Cherenkov radiation in the conventional case when you have index of refraction equals to 2, sorry, with a velocity of the particle equals to 0.6, the speed of light. And you also have the Cherenkov cone in the Carroll case, but this Cherenkov cone is shifted away from the standard Cherenkov cone one would expect if we have conventional matter. So and also this angle is larger than the conventional Cherenkov angle. And the more interesting case is when you can have 2 Cherenkov cones instead of 1. And these 2 cones are shifted away from the standard Cherenkov cone. And this is better. You can look this better with this plot. We have plotted the H function, and we have cut it with different velocities of the particle. You have the red region that corresponds to a case when you have Cherenkov radiation, even though you may not have Cherenkov radiation in the conventional case. For comparison, we have put this H class function to compare the region when you can have Cherenkov radiation, and the H plus and H minus correspond to the regions when you can have the Cherenkov cone with theta described by theta plus and the Cherenkov cone described by theta minus.
So what are the realistic values of this theta parameter? Let's say for existing.
They are very small. they actually corresponds to around 10 to the minus 2, minus 1, that's what we call it. But if you have index of refraction like 2, from 2 to 5, they are very small. So the beta is small. So it's a, well, in the nowadays realizations, I don't know if you can have, if you will be able to obtain more experimental realization from semimetals that have a bigger cognitive constant P, but up to now they are very small.
Yeah, my expectation is the following. So beta will be a measure of the separation between the two zero points in the momentum space. The separation can be light enough, of course, but it cannot exceed the reciprocal space. And so when you approach the boundaries of the Brillouin zone, this continuous medium treatment, or effective medium treatment, becomes negative, so you have to consider the periodicity of the crystal and solve a bit more complex problem of radiation with periodic structure. This was, I guess, people try to look at it, but that's a different problem. In a sense, if you are adopting effective medium treatment, then there is an upper limit, a soft limit on this beta problem. If we cannot go too far.
That's lucky for us because we make this beta smaller than 1. To obtain this calculation, you have to remember the beta is smaller than 1. And actually, in the nowadays realizations, it's way smaller than 1. So this is still a good approximation. Okay, you have 2 regions. One we have Cherenkov radiation, one cone, and second cones. Also, we can calculate the Cherenkov angles, the capacity of the minus as a function of the parameter beta. And we can see that when beta is large enough, we cease to see the second Cherenkov cone. It gets too close to 0 and goes away. This can be calculated analytically, and I produce some functions, as you can see. Now, these are the plots of the distribution of radiation. This is for the vacuum Cherenkov radiation. It is a refraction equals to 1. We consider a wavelength of 450 nanometers that correspond to blue light, and the speed of the particle 0.85 speed of light. In the panel A, we have a parameter psi that I told you of 4.5 micrometers, and in the panel B, it was 200 micrometers. So we can see the emergence of the cone when you make this parameter larger, which is by taking into account more distant trouble by the curve. So yeah, it reproduces the Cherenkov cone and gives us exact beautiful images. This is for vacuum Cherenkov radiation. This is the case that I told you that the chiral Cherenkov cone is shifted away from the standard Cherenkov cone. One would expect if we didn't have chiral material, if beta is equal to 0. This is for these parameters, most kind of the same, but with index of refraction equals to 1. So we allow to have index of refraction. And for consistency, we have made the parameter every time smaller. And we can see as we make the chiral parameter beta smaller, Cherenkov cones get closer and closer. So when this approximately 0, they go to the same direction we will expect for the standard Cherenkov radiation. So all our results are consistent with one we expect from to obtain in the nice limits. Now to finalize the calculations, we study the total radiated energy with respect with this ratio is the total radiated energy by the loads given by plus or minus loads, with the standard Cherenkov total radiation. So we find out that the contribution to the radiation for the theta plus cone is always bigger than the inner cone. This is another plot that tells you the same thing. And if at some point you cease to have you don't have anymore the second Cherenkov cone when beta is larger. And since we have studied not only Cherenkov radiation in chiral matter, but also we can study the vacuum Cherenkov radiation when we make n equals to 1. We check our results with literature, and we compare our results to the vacuum Cherenkov radiation previously studied in literature by Chiral Cherenkov from Iowa University. He uses quantum field 3D methods and obtain another propagation within the dissertation. Where this theta, this script theta, is the angle of the movement of the particle with respect to the vector v. We remember that all these results were done by considering a movement of the particle parallel to the vector v. And also the lambda, it corresponds to the right-hand polarization. So also, I told you that the plus sign corresponds to the right-handed polarizations, but we haven't confirmed it more rigorously. And if we make these results, we obtain this angle of radiation for the vacuum Cherenkov radiation. And our results, if we make our particle, relativistic particle with velocity equals to 1, we consider very small angles on very small parameters, we obtain the results immediately. So our findings contain previous results in the limit case and experimental detection of Chiral Cherenkov. Well, we expect that this Cherenkov radiation, these Cherenkov angles can be measured by sending a fast charge through a slab of material by using a Cherenkov culture. And moreover, calculating the measurement of the theta plus angle provide an experimental optical determination of the parameter v. But one has to know the direction of this v. And if you measure the theta plus angle, you can extend the separation of pi nodes in this material. Recently, there have been realizations of action response in multi-layer metamaterials. And not only, these realizations of these multi-layer metamaterials, one can have gradients of action response that corresponds to the vector v. So, hopefully, we won't have to wait 4 years to experiment the detection of this effect once these designs of materials get produced and estimation and something. So, to conclude, we have established the factory approximation for the Green's function for chiral matter characterized by the vector v. In the case where beta, our parameter, is smaller than 1. We apply these results to the case of a charged particle moving with this chiral medium and high constant velocity parallel to v. So we conclude that the Green's function using suitable approximations allows to obtain analytical forms to study modifications of radiation in chiral matter. The Cherenkov radiation, the index of refraction is bigger than 1, suffers modifications such as the shifting or splitting of the Cherenkov cones. And our results are consistent with the limit case of vacuum Cherenkov radiations that occurs when the emission refraction is proximal. So we expect that our results will provide the basis for studying further processes such as the Cherenkov radiation with charge traveling at arbitrary direction with respect to v. Also to study radiation losses and synchrotron radiation, etc. We need to do further study on the polarization of the light emitted for experimental detection. And furthermore, we have to relax the condition beta to describe for material with a stronger magnetic field. We are now in a position to study the radiation for arbitrary time-dependent localized sources. And this will develop interesting research applications in quantum plasma, biosimimetals, and actually that. So finally, I want to acknowledge my master's advisor, Dr. Luis Grandurutia, and also our colleague from Brazil that helped us to put our results in an article that is submitted to Physics Review B, and recently have very good comments, and we hopefully we'll have this paper published this year. So thank you very much.
Thanks, Don. That's not that publication. Yes, please.
Can I?
Yes, please.
Yeah, thanks for the very interesting talk. So my question is the following. So you mentioned first the Weyl semimetals, didn't you? And then you took the refraction index. That means that there were no absorption inside the medium, right?
Okay.
So this is where I'm a bit confused. So if you're talking about metals or semi-metals and then there is no absorption, so how does it work then?
Oof. Questions. I don't know. I think it is. For me, it appears that there is no radiation losses. But for example, on these nice plots of the total radiated energy, we can see that with respect to the standard Cherenkov radiation is different. So we may have losses, but we don't. Maybe these losses are within the material, but I don't know how this works.
Maybe, Dmitry, I could comment a little bit on your question, even though I'm not educated about semimetals. So, as far as I understand, people say semi-metal because, from one hand, we don't have a bandgap here, we have just a zero. And in this sense, no bandgap, it's not dielectric, so that's why they call it semi-metal. But the material realization would be different. So, in condensed matter, for example, structures, we can do some additional structures, which also behave as wild semi-metals. So the losses are not that high necessarily. But of course, the effect that losses should be estimated. As far as I understand, this calculation is. But I'm not involved in this book, so I don't know. Yeah, it's my guess.
Yeah, Max, thanks. So it's a general comment. So I have no objections whatsoever about this very first step. Yeah, the only thing is that I think you should compare the absorption length inside this very material compared to the radiation formation length, right? And then so if the radiation formation length is less than the absorption length, then it makes sense to speak about the Cherenkov radiation.
Thank you for the comments.
Thanks, Nick. So, following up on this discussion, so Eduardo, how many cones of Cherenkov radiation would you expect if the velocity of this charged particle is not parallel to the B vector?
We still have refractions, this radiation, but I start doing the calculations, but I can't yes, but I don't know. I haven't finished the.
Yeah, of course, I understand that you don't have an answer currently, but maybe a bit guess. So, in the case of an inappropriate medium, as you said, and as we know, you might get
probably. If we have an angle between, yes, we will have two cones also, but I would like to say that the cones would be like like the form. And because there has been a study of Cherenkov radiation in bioscopy, this is not new. I mean, we have got all papers that actually do the calculations, and apparently when you have a refractive material like this, this is effectively refractive. One can obtain two cones, but they are deformed somehow depending on how refractive they are. So probably yes. In this idealized case, when you have the particle traveling parallel to the electron beam, you have circular cones. I would expect them to be deformed somehow.
Okay. Yeah, maybe it's reasonable because in the case of some arbitrary medium, we still have two modes, two transverse modes with limited polarization or something, and this each of the eigenmodes corresponds to the individual pole. Yeah, in a way. Good. And then one more question. So you conjectured that potentially these Weyl semimetals could be exploited for Cherenkov detectors. Could you elaborate more on this? So it's just
it's that I thought we have you know, maybe you have realizations of these materials. I think before detecting particles with these semimetals, I think it would be more useful case for measurements, optical measurements of the parametry rather than detecting particles, I say.
Right, because in my understanding, the easiest way to extract the magnitude of B is just to do some calculation of the band structure. If it is solid state polarization, then we need to do DFT, then identify the positions of the different points, and then explicitly take the difference in momentum, and then you get the answer.
Yes, if you come with this method, we call admission.
Yeah, admission. Absolutely. Or if it is photonic realization of Weyl with a semimetal, then it's easier, then you run some console simulation, give the positions of the different points, so it's fully the standard. Fine. And then maybe the final question, maybe technical one. So you wrote the constitutive relators for CFJ-electrodynamics in the form as induction case. So you have theta which depends on S. So can we go to that slide, please? Okay.
Yes, I just write it for the Axion case.
Yeah, so it's on the left-hand side. So what happens if we try to write our constituent relations with this theta, where theta is proportional to E times X?
Yeah, you have, for example, H state equals to B, and D have a B0 component and B vector component. Like,
yeah, so in my opinion, this is a bit problematic because, as you said, there are solutions in the form of plane waves in these Weyl semimetals.
Something like this, but with probably omega here and here. So I don't know. But I have.
Yeah, in the form you wrote, it's perfectly fine, but there is some issue here because your theta depends on X, and in a way, when you substitute deltas in the form of plane waves, you get some problems.
Yeah, but these are things directly from this can be obtained directly from this
on the right hand side.
Yeah, so but I have answered the question there. Yes, obtaining this from these ones. I think not, because I haven't done this way. Maybe there is a reason why, but
yeah. So the form on the slide on the left hand side is a bit problematic. But the form you're writing on the whiteboard, if you can finalize. So how do you write the equation for H?
H is equals to the other. If I remember correctly, this is 7. I maybe I have some play, but I don't have it right now with me.
Yeah, I guess this can be verified.
Yes, it's not that easy to calculate these positive relations.
this form of constitutive relations is perfectly fine. Now I understand. So any questions from the audience? Please,
Yeah, just a general question, also maybe regarding relations. So if you take some medium that is defined by such constitutive relation, you call this Carroll-Field-Jackiw, right? And there is also a simple Carroll medium that, for example, consists of Carroll molecules. I wonder what.
Okay. Yes. Yeah. With Carroll molecules, we say this words. I would say this won't work. I think because I mean I refer to this as Carroll model. I made some mistakes like referring to this also as Carroll media, and this is very about clarification that Carroll mediates with Carroll molecules. For example, water with sugar. This case, Carroll model is materials that have this electromagnetic response. So I would say Carroll molecules will give you this effect unless the nanostructure is like this.
Yeah, but they have like similar relations, but I didn't not really understand what's the difference.
Please.
So, can you show the previous slide? This relations.
This one?
Yes. So for Carroll media,
yes.
You put imaginary factor before instead of this.
You mean
it's a specific case of bias-tropic media.
you have like a complex
And now you're
for Carroll model, yes, is purely yes.
So maybe I can comment. It's a bit an issue that in the terms of so media here in electromagnetic we call Carroll media is special invariance. So this story is a bit different, and the difference comes from the different behavior on the tangents. In particular, the vector, as far as I can see, is formed on the tangents. So you need to draw cards by tangents. In the case of Carroll molecules, it's sugar molecules within. So this brings in a bit different physics, at least from my understanding. I personally was asking regarding during our first meeting exactly the very same. Fine. Oh, it's equations in the Zoom. Okay, so let's thank our speaker once again. And the Lord is around, so in case you get any ideas of where you can please work, feel free to contact him anytime.
Thank you very much for coming here.
Yeah, thank you, and see you at the next seminar, which is in a week. As far as I remember, we have some guests, so not our internal people, but people from outside. Please spread the announcement and see you next time.